Let's do the explanations one by one now. So what are we trying to do? We are trying to explain the unstable ice age carbon cycle, basically saying that there is a positive feedback between carbon and temperature changes, whether you are building ice glaciers or whether you are melting them. People use the lead lag between temperature and carbon to argue that CO2 has nothing to do with the warming, but that's a little silly. So that was the idea of looking at the phase lag and lead, and then see how carbon builds up and builds down. The main story will be to start by explaining why we think ocean is needed to play a much bigger role here, even though the ideas keep evolving that maybe there was stagnant buried carbon on land that got released after the glaciers retreated. So this is a debate that goes on. The main thing for the ocean is to start by looking at how a colder temperature could have done it. But first, let's say why ocean is being invoked as the major player. If you look at the evidence of carbon isotopes in corresponding to the atmospheric CO2 change during the ice age, the last one is the best one we have, right? So 21,000 years ago or so, the last ice age reached its peak, and then it started melting. It had these hiccups of younger Dryas, older Dryas, and so on, and then we came out into the Holocene. The evidence suggests that the carbon in the atmosphere at the time had a slight deficit, about 0.3 parts per thousand of delta C13 being less. If to explain this, you cannot invoke more production of organic carbon in the let's say on land, because when photosynthesis happens, there is a 25 parts per mil deficit of delta C13 created in the organic carbon, because they are taking up more C12, which means the CO2 left in the atmosphere will be heavier, because the photosynthesis is locking up the lighter CO2 and increasing the weightier fraction of the CO2 in the atmosphere. So that's not going to give us the right direction for explaining the observed isotopic signature. And this means that even you can do the same for ocean biological production, which we will come to. There are many factors involved, but the long story short is that we somehow need the inorganic carbon to do most of the work which is done in the ocean. But as I said, there are papers which argue that there was a stagnant pool of carbon on land that was buried under ice, and then that got released after the glaciers retreated. But if we want to do it by the ocean, what are the main features we're going to look for? One of the biggest ones is, of course, coming back to this Atlantic Meridional overturning circulation, which we will look at again soon, where you have water sinking in the North Atlantic, in the Greenland, Iceland, Norwegian seas or Jin seas, and then you have water sinking in the Southern Ocean, Ross Sea, Weddell Sea, and so on. Slightly different processes, as we will see. And this is basically this involves basically taking down the heat, the cold waters and the heat in the North Atlantic, moving it south across the equator below the surface, mixing it with the Southern Ocean, and then moving it into the Indian and Pacific Oceans, where it becomes surface water on hundreds to thousands of years of time scales, and comes back across the equator into the North Atlantic near the surface. I will show this figure again, which we already looked at. So this deep water sinking, or North Atlantic deep water sinking in the North Atlantic, and the Southern Ocean circulation and inundation of the Indian and Pacific Oceans together is argued to create this so-called bipolar seesaw as well, which you can see here. So you can see that there is somewhat of an out of phase temperature relations, let's say, between Antarctica and the Greenland region. So you have delta O18 again corresponding to cold and warm periods, and you can see there is a approximately 1500 year kind of oscillation, not a perfect one, but nonetheless you can see that the what is often referred to as the bipolar seesaw is seen in the Greenland and Antarctic records. So I'm kind of waving my hands through it because these are really, as I said, evidences seen in the data but not explained very well in terms of the physics, because we don't know where this 1500 year time scale would come from really. Okay. Nonetheless, looking at the Atlantic Meridional overturning, we have the Labrador Sea and the Jin Sea deepwater formation sites. I didn't mention Labrador Sea before, sorry. So you can see the water sinks. Basically, there is plenty of evaporation here because the Gulf Stream and this cross-equatorial transport of the warm surface water in this orangish line creates a warmer ocean, and the atmosphere above gets warmer compared to, let's say, the North Pacific, and that allows evaporation to load up the moisture in the atmosphere, leave the salt behind, and create denser waters, because if you cool the waters by evaporation and leave salt behind, you're going to increase the density non-linearly. The density of seawater is a non-linear function of temperature and salinity. So that sinks, and this blue water is blue arrow is blue color is what is the southward flowing subsurface deep water, and there are intermediate waters as well. You can see the intermediate return flow in green colors and the warm surface waters here. So that is mixing with the deep water formation regions in the Southern Ocean shown here, and because the Southern Ocean is a channel, the water can circulate several times and eventually go into the Indian Ocean, which is landlocked here. So the water becomes surface water and comes back out by mixing with the surface waters forming in the Pacific, coming across through the Indonesian seas in the Indonesian through flow, then going across here south of Africa back into the North Atlantic, and you can see the the Pacific surface and subsurface circulations here. Okay, so if solubility of the ocean, so cold waters hold more CO2, right? We are trying to draw down CO2 by 80 to 100 ppm during the glacial times. If the ocean got substantially colder, then maybe you can draw down more CO2, just like a Coke can. You keep it cold and sealed because high pressure and cold temperatures are needed to hold CO2 in a dissolved form. If you open it or keep it in a warm temperature, it's going to lose the fizz, right? So could you have cooled the ocean substantially? It is possible that the North Atlantic, the northern hemisphere, which was heavily glaciated and probably covered with sea ice and so on, was not able to form so much deep water. There are evidences of changed Atlantic meridional overturning during the Ice Age, which would fill the deeper ocean with more of the colder Southern Ocean Antarctic bottom water, which is the heaviest water that sinks to the bottom, and the North Atlantic deep water is on top of it, and then the Antarctic intermediate water is on top of it, and so on. So presumably you could create a colder, deeper ocean, and there is evidence that the deep ocean, which is now at -2 degrees centigrade on average, was at -3 degrees centigrade then. You can go below freezing because you have salt, which prevents the water from freezing, right? So that's what would happen. Does this idea work? Well, it turns out that the solubility argument of increasing colder waters and increased dissolution of CO2 into the atmosphere during the ice age does not give us enough of a drawdown. Okay, you can do the numbers in terms of how much CO2 slug you would need to create this minus 0.3 parts per mil deficiency of delta 13. That amounts to about 500 gigatons, and you could not have pulled down 500 gigatons of CO2. This is just showing the warmer sea surface temperatures here and higher salinities in the Atlantic, especially compared to the North Pacific. In fact, the air temperatures here are 10 to 50 degrees cooler than the same latitudes over here. UK, for example, is mild temperatures, drizzly weather, whereas you get here really miserable, cold, snowy, icy winters. So that's related to this thermohaline circulation, the Gulf Stream, and the inundation of that into the Gin Seas and Labrador Sea, and so on. So this cross-equatorial seesaw can be created by how much energy is moved across, and that can give you a 1500 year time scale, but it's not very well explained. There are other explanations which are so this is just showing the same thing in warm stadial and cold warm interstadial and cold stadial conditions, and you can see the differences here in terms of warmer waters inundating and creating meltwater, whereas it's colder here in the cold stadial conditions. So AMOC, or Atlantic Meridional Overturning, remains a prime candidate for this, but newer arguments also include now in terms of how the zigzag of the jet stream varies, and there is some evidence that global warming and loss of sea ice over the Arctic is creating changes in the jet stream pathway, its meandering and invasion of colder Arctic air to the south, and invasion of the warmer subtropical air to the north, and so on, creating very warm Fairbanks, Alaska, and very cold Washington, D.C. at the same time, and so on and so forth. Okay, so that is also related to ocean conditions, even though atmospheric processes are riding on top of it. So ocean can play a critical role, but the first hypothesis that colder ocean and increased solubility could have played a role cannot really explain 80 to 100 ppm CO2 change we need from the ice age to the deglacial age, or the Holocene, and the other way in the previous ice ages. So I will leave this here as the first hypothesis that doesn't work very well, and then we will move to the next hypothesis on whether biology could have done it.